Hey everyone, this is Shubham, one of the odds from the oddballs. Today, I'm going to discuss about this query: is SUPI concealment really ensures forward secrecy? Before that, you should have a prior knowledge of the 5G code and 5G security, especially the 5G AK procedure, which includes the SUPI concealment and ECIS scheme. So these are some of the terms and topics that you need to be familiar with before moving forward. So let's understand each of them through some formal definition from the internet. Forward secrecy or a perfect forward secrecy. It ensures that the session keys will not be compromised, even the long-term keys are. It protects the previous sessions and the compromission will only limit it to that particular session. If I have to sum up this all highlighted part in one definition, it states that if a long-term key gets compromised, it would not affect the previous sessions by any means. In other words, the previous session encrypted data will not be decrypted by the attacker if any long-term key gets compromised. So let's understand what is the difference between the session key and the long-term key. A session key is a temporary key that is regenerated for each session, and it is not intended to be stored. One such example is ephemeral keys, which are temporary keys and are only limited to that session itself. Whereas on the other side, we have a long-term key that is used for multiple times at multiple instances for the security purposes, and it is intended to be stored somewhere for further use in the future. Then on the series, we have the public key cryptography or asymmetric cryptography. In this cryptography, it generates a key pair consists of public key and a private key. As the name suggests, private key is kept secure with the user, whereas public key are intended to be openly distributed on the internet. One more thing is that about the public key cannot be used to regenerate the private key. No one can regenerate the private key from the public key itself. So that is the major advantage of the public key cryptography. Then we have the ECDH, elliptical curved Diffie-Hellman in the series. So it states that it is a kind of key agreement protocol that allows two parties, each having an elliptical curved private public key pair, to establish shared secret over an insecure channel. This is public private key pair is again the public key cryptography. Let's understand this elliptical Diffie-Hellman for an example because it's kind of a vague definition. It would be more proper if you understand through a diagram. So in this particular diagram, there are two parties, Alice and Bob, each having their own private and public keys. Then further, they share their public key over this insecure public channel and use the other party public key and their own private key to generate a shared secret or shared key, which they are going to use to encrypt the further messages. They are used to encrypt the messages further discussed between them. Then further, we have ECIS. Before 5G in 4G, user identity (IMSI) is shared as a plain text over the internet, which prone to the attacks such as man-in-the-middle attack, in which the third party catches the IMSI of the user and use it for the malicious purpose. So to encounter this, TGPP introduced an encrypted form of user identity in 5G, which is called SUCI. ECIS scheme is nothing but a technique or an implementation that uses some symmetric key encryption and various ciphering algorithms for the conversion of SUPI to SUCI and vice versa. Let's understand the call flow of ECIS scheme. So this is a whole call flow of ECIS scheme. So first of all, we generate a key pair for the home network. using some cryptography, let's say elliptical curve. So in this cryptography key generation, we have an home network public key and home network private key. Remember this, these are the long-term public key and the private key. Then the long-term public key is pre-installed by the operator in the 5G SIM, which is then installed on the mobile devices, which is UE. Then the home network private key is stored in the UDM, which is the network function responsible for SUPI concealment in the 5G code. Then on the UE side, we generate a fresh ephemeral key pair for a particular session using some cryptographies such as curve 25519 or SAP256R1 based on the profile we use. Then further, we use the ephemeral private key and the long-term home network public key to generate a shared secret based on some key agreements such as electrical curve 𝗲𝗏. Then similarly on the UDM side, we use the ephemeral public key and the home network private key to generate the same shared secret. Ephemeral key is publicly shared over the internet. Then this shared secret are further combined with the ephemeral public key and passed through a key derivation function to generate this AS key and a MAC key. This AS key will be used for the concealment for the encryption and the decryption of the SUPI, which is the user identity. The MAC key is then passed to a hashing function HMAC SHA-256 to generate a message digest on both ends. This will be needed to verify the integrity of the message over the internet. Now, if we focus on the generation of shared secret, which looks like this, so we would understand that for the generation of shared secret, we are using the public key of other party and the private key of itself on both ends to generate a shared secret. If I have to show this through a call flow, it would look something like this. So UE is generating an ephemeral key pairs, which is public key ephemeral key and the private key ephemeral key. Then we are having some kind of key agreement, let's say electrical curve 𝗲𝗏 between the public key of home network and the ephemeral private key to generate a shared secret. Then sharing of the ephemeral public key over the internet to the UDM. Then UDM again undergoes the key agreement between the public ephemeral key and the private home network key to generate the shared secret. Here I shows the attacker in between the UE and UDM. So we are assuming that there's attacker who are eavesdropping between the UE and the UDM and is able to capture the ephemeral public key. So as per the definition of the forward secrecy, if any long-term key, let's consider the home network private key, gets compromised, the previous session should not be compromised. But in this case, if the home network private key gets compromised, the attacker will use the home network private key and the ephemeral public key of the GUI to generate the shared secrets as generated by the UDM. So here in this scenario, we can say that even though we use ephemeral keys, the forward secrecy is not maintained. I have a question for you guys. Is incorporating ephemeral keys will bring the forward secrecy? If you search on the internet, it says yes, but a broad aspect is left behind. That is how we use it is also important, because in the current scenario, we saw that even though we use ephemeral keys, the forward secrecy is not maintained. So I have a proposed solution how we can maintain the forward secrecy in the current scenario. So in this proposed solution, what I'm doing extra I'm also generating an ephemeral key pair on the UDM side. So beforehand that everything is same. We're generating the ephemeral key pairs on the UE side and using the key agreement between the home network public key and the ephemeral private key to generate the shared secret. But this time, we're generating ephemeral keys on the UDM side as well and share the public ephemeral key on the from the UDM side to the UE. Then UE is using the ephemeral public key of the home network, which is the UDM, to encapsulate its own ephemeral public key to generate the ciphertext. This ciphertext is then shared with the UDM. Then UDM will decapsulate this ciphertext using its own ephemeral private key to regain the ephemeral public key of the UE. Then it further goes to key agreement between the ephemeral public key from the UE and the home network private key to generate the shared secret. One important note for you to get that in the electrical cryptography, it is not possible to encapsulate or decapsulate because it does not work like the RSA. So in order to do that, you need to use the HPKE, which is a hybrid public key encryption, to use the functionality like encapsulation and decapsulation. So in this particular case, the attacker has access to these two keys, the public ephemeral key of the UDM and the ciphertext. And by the definition of forward secrecy, if any long-term key, the home network private key or the public key, gets compromised, attacker cannot deduce the shared secrets based on these four keys by combining them in any form. So we can say that in this proposed solution, the forward secrecy is maintained. However, I have a question for you that is in the SUPI concealment really requires forward secrecy? Because by the definition of forward secrecy, if the long-term secrets gets compromised, previous session should not be affected. But as you can see, each time in the SUPI concealment, each time the same data, which is SUPI, is traversed in the encrypted form. If it gets decrypted in any session, there is no need to decrypt the previous sessions. So we can say that ensuring forward secrecy in the SUPI concealment is not enough to ensure the security of the 5G. We should be focused more on the security of the session keys itself, because those keys are going to be used further for the message exchange between UE and the UDM. And apart, if you find this solution interesting, I would love to hear your thoughts in the comment section. And I'm also sharing the link of this blog so that you can also read and share your thoughts as well and connect with me. Have a good day. Bye. See you.